Alright, so summer is almost here, which means we need to worry about making s'mores. Naturally, I'm sure that's the most prevalent thing on your mind right now. Not COVID, not anything else. So let's say that we are like normal people and we write a chemical reaction when we make our s'more. So for me, let's just say that it's going to take 2 graham crackers and 3 squares of chocolate and 1 marshmallow to make my 1 s'more. So there's my balanced chemical equation for making a s'more. Now, I don't know if you've ever experienced this or not, but when you're making s'mores or some other treat, something always runs out. Okay? Something always runs out, and then you always have a whole ton of excess other stuff, and you always sit there going, well, what do I end up doing with all this extra stuff? So usually with marshmallows, you end up with just, s'mores, you end up with just a ton of marshmallows. And then you eat marshmallows, just plain, which isn't terrible when they're toasted, but still, it's not as great as a s'more. But I digress. The whole point of this limiting reactant problem is to determine, in very real terms, how much product you're going to be able to make based on the quantity that you have of your reactants. Now, the word limiting is fairly self-explanatory. Reactant, that is as well. You'll also hear this referred to as a reagent. Same thing, okay? What this basically means is one of these things is going to run out first. Okay, one of my reactants is going to be used up or consumed first. When that happens, I can no longer make my final product. Now, you and I both know that we can still make s'mores without chocolate, or even if we have to without graham crackers, although then it's really just a marshmallow. But for the purposes of a chemical reaction, as soon as you run out of a reactant, you're done. Okay? So let's just say that I have available 50 graham crackers and 60 chocolate squares and let's just say 70 marshmallows. Okay? That's what I have in my pantry that I pulled out, that I took out to the fire to make s'mores. Okay? Which looks like a lot. Alright, but let's see how many s'mores we can actually make. So according to my chemical reaction, I can do stoichiometry because, again, this is what normal people do, people. This is what we do. Okay? It takes 2 graham crackers to make 1 s'more. Okay, so I have enough graham crackers to make 25 s'mores, which is sounding good so far. Okay, if anyone can eat 25 in one sitting, frankly, you probably have problems. And then, according to my reaction, I need 3 squares of chocolate to make 1 s'more. Okay, 60 divided by 3, that's going to give me 20 s'mores. So already you might be seeing a problem. Okay, I did have enough graham crackers to make 25 s'mores, but I only have enough chocolate to make 20 s'mores. Well, let's check on the marshmallows. Marshmallows, it only takes 1, although some of you may use 2, and I'm not here to get into an argument about that, to make 1 s'more. So I have enough marshmallows to make 70 s'mores. Okay? But our question is, can I actually go outside and make 70 s'mores? No. Okay? This number is not possible. Nor is this number even, if I'm following a strict recipe for s'more making. In reality, I will only be able to make 20 s'mores. Okay? And this means that my chocolate is what is referred to as the limiting reactant. Okay? It limits the progress of the reaction. When this runs out, okay, I'm done making a purist version of s'mores. Okay? That makes these two, the graham cracker and the marshmallows, that makes them excess reactants. Okay, so those are things that I have more than enough of. And when the reaction is over, in other words, when the chocolate runs out and I've made 20 s'mores, I'm going to have extra graham cracker and I'm going to have extra marshmallows. Okay, so far we've answered 2 questions. 1, how much product am I actually going to be able to make? What is the limiting reactant? Okay, in other words, what's going to be used up? And then I can take my excess reactants and find out a little bit more information. I'm going to focus on the marshmallows. The next question that might be asked is how much excess reactant will be left? Okay, actually I'm going to focus on the graham crackers. I think that's better. So let's put it this way. I know that I will make 20 s'mores. Okay? And in order to make a single s'more, according to my equation here, I need 2 graham crackers. So for every 1 s'more, that's 2 graham crackers. Okay? So that's 40 graham crackers. This quantity right here is how much graham cracker I actually used, I'll even write that in, actually used to make my 20 s'mores. Okay? However, I started with 50 graham crackers. This was my initial. Okay? What I'm going to do is subtract the 40 graham crackers that were used, okay, and this will give me 10 graham crackers in excess. Okay, I could do the same thing with the marshmallows, but you can probably just look at it and realize, oh, you're going to have 50 marshmallows left over. Okay, so this is your excess reactant, and this is your super duper excess reactant. All right, so that's the concept of a limiting reactant problem. In other words, when is the reaction going to stop because I run out of one of my reactants? How much product am I actually able to make, and how much of my excess reactant is going to be left over? Now, it's not quite as simple as all this when we throw in actual chemicals, because we need to worry about things like molar masses on top of these ratios. Okay, so let's jump into a real problem. Stalling, flipping paper, and now we're good. Okay, so here's an actual problem. We've got 15 grams of aluminum oxide that need to react with 18 grams of fluorine. So that's what I have available. That's what I'm throwing into my system, okay, to react. Up till now, you've just had something like this, where 15 grams reacts. How much am I going to be able to make? The assumption that you're making there is that all these 15 grams get used up. We cannot make that assumption when we have 2 different reactants with specific quantities. Before, we were assuming that the other reactant was in excess. Okay, now we have specific information. So there's a few questions that we want answered. How much oxygen is produced? Okay, first thing we're going to need to do is write a balanced chemical equation. What is the limiting reactant? Okay, is it aluminum oxide or is it fluorine? How much excess reactant is left over? So if the limiting reactant is aluminum oxide, how much fluorine is left over, or vice versa? So we haven't done the math yet. And then finally, what is the percent yield of the product if 5.6 grams of oxygen are collected in reality? Okay, so we take our stoichiometric answer from this question right here and do some math. So the first thing that we need is a balanced chemical equation. So we've got aluminum oxide, that's going to be Al2O3 reacting with fluorine, F2, of course. We're going to make aluminum fluoride, so that'll be AlF3. And then we'll kick out oxygen. So this is a non-metal single replacement reaction. All right, of course, we're going to need to balance. So let's see. We're going to need, we're going to need to double this. So 2 of those, which means 4 of these. Okay, which means 6 of these. And we've got, that looks good. 3 right there. I'm going to go ahead and add in my molar masses, just so I don't have to think about this later. So 101.96 grams per mole for the aluminum oxide, 38 grams per mole because it's diatomic. I think I made a mistake in earlier notes. I didn't make the molar mass diatomic for like oxygen or something. I do apologize for that. 83.98 grams per mole aluminum fluoride, and then, oh, there it is, 32 grams per mole for oxygen. Okay, so here's what we know. We have 15 grams of this stuff. We've got 18 grams of this stuff. In fact, I'm going to write it like this. Here's my start. Actually, I like initial better. Here's my initial. This is going to be what I use. And then what I have at the end. Okay, so I know that I have 15 grams of aluminum oxide and 18 grams of fluorine. And of course, at the beginning, I have no product whatsoever. Okay, so I'm going to take my 15 grams of aluminum oxide and 18 grams of fluorine, and I'm going to do some stoichiometry. Now, this problem specifically asks for how much oxygen is made, so I'm just not going to worry about my aluminum fluoride at all. I am just going to focus on my oxygen. Okay, so what I'm going to do is take these two quantities, and just like we did with the s'mores, we converted our marshmallows and our chocolate, etc., into s'mores. I'm going to take my two reactants and I'm going to convert them into moles of oxygen and see how much I can make, if assuming I'm able to use up all of either chemical. So, grams to moles, use molar mass, 101.98 grams of Al2O3 per 1 mole. And then I need to use my mole ratio, so for every 2 moles of Al2O3, I'm able to make 3 moles of O2. And of course, those come from my coefficients in my balanced chemical equation. Okay, so if I throw that into my calculator, I'm able to make 0.221 moles of O2. Okay, that's if I get to use up all 15 grams of Al2O3. That happens if I have fluorine in excess. I don't know that yet. I gotta find out. So I'm going to do the same thing with my fluorine. I'm going to convert it into oxygen. If I use up all 18 grams of fluorine, how much oxygen can I make? So, not 18, sorry, 38 grams of F2 for every 1 mole. Okay, and then mole ratio. Now, this gets used up faster. So you might go, oh, 18, that's going to be excess. Well, maybe. You have to realize also, look at the coefficients. Fluorine gets used up 3 times faster than the aluminum oxide is, so we don't know that yet. So, for my coefficients, for every 6 moles of fluorine that I use, I'm going to produce 3 moles of oxygen. Okay, throw that in my calculator and I get 0.239 moles of O2. Okay, so now I've got some figuring to do. I need to compare these two numbers. If I use up all 15 grams of Al2O3, I'll be able to make 0.221 moles of O2. If I use up all 18 grams of F2, I'd be able to make 0.239 moles of O2. This number's bigger. This would be nice, but in order to make 0.239 moles of O2, I would need more aluminum oxide. So what this means is my aluminum oxide here is my limiting reactant. It can make less oxygen before it runs out, so it is the limiting reactant. So guess what? I get to answer one of my questions. What is the limiting reactant? Oh, Al2O3. In this scenario, with this ratio of masses here, Al2O3 will run out first. Now this question up here asks how much oxygen is produced. Well, I know moles. Let's convert that into grams. So I'm going to take this number right here. This is my real number. Okay, this is a fake number. I'm never going to be able to make 0.239 moles of O2 because Al2O3 would have run out. I'm going to take 0.221 moles of O2. Molar mass of O2 is 32 grams per mole. Okay, and I will be able to make 7.07 grams of O2. So that's how much I actually made, how much oxygen I actually produced, 7.07 grams of O2. Alright, so I can fill out my chart a little bit more here. I know that I produced 7.07 grams of O2. I know that since aluminum oxide is my limiting reactant, I know that I use up all 15 grams. So I'm going to be left with 0 at the end. That's what this E stands for, end. Okay. Now there's two things I don't know. I don't know how much fluorine I actually use, and I don't know how much is left over because I don't use all of it, right? There's going to be a little bit left over. So that's my last goal here, to figure out how much fluorine I use and therefore figure out how much is left at the end. Now there's a few different ways that you could do this. Okay, I'm just going to go over one. You could probably figure out others. So I have identified that fluorine is my excess reactant. Okay, so I was able to make in this reaction 0.221 moles of O2. Okay, that is a fact, that is known. I'm going to take this number here and I'm going to solve for fluorine. Alright, so I'm going to go backwards. So for every 3 moles of O2 that I produced, that means that I consumed 6 moles of fluorine, and then I'll use its molar mass, which is again 38 grams per mole. Okay, so there's my molar coefficients right there. Okay, and if I do that math, I end up with 16.8 grams of F2. Now let's think about what this means, because at this point there's just lots of numbers flying around and you don't want to get confused. I made this much oxygen. Okay, in order to make this much oxygen, I had to use up 16.8 grams of F2. So this is what was used. Okay, so I can even add that into my chart here. I used 16.8 grams in order to produce 0.221 moles of O2 or 7.07 grams of O2, same thing. Okay, I just skipped a step here because why do it twice? So what I need to do now is remember that I started with 18 grams of F2. That was my initial amount. This is what I started with. This is what I threw into my reaction system. I just determined that in order to make 0.221 moles of O2, I used 16.8 grams. This is what was used. Okay, so if I subtract those two, I end up with 1.2 grams of F2, and this is my excess. This is how much is left at the end, so I can fill this out right here. At the end of this reaction, I have no aluminum oxide left over. It was my limiting reactant. It's gone. I still have 1.2 grams of F2 left over, which is not bad. Okay, I didn't waste a whole ton. And in order, or at the end of this reaction, when these have all been used, I will have produced 7.07 grams of O2, and yes, some unknown quantity of aluminum fluoride, but I could figure that out, but the question just asked for oxygen, so I didn't bother. The last thing we want to know is, let's do this reaction. We figured out all this math. We did the stoichiometry. We know what we want to do. We go into the lab. We actually do it. And at the end, we only collected 5.6 grams of oxygen. Now, there's lots of reasons for that. User, just, I hate that I almost said user error, but maybe your setup isn't great. Maybe you lost, oxygen gas, that's going to be hard to collect. So maybe you have a leak in your tubing, something, okay? Impure reactants or impure products, anything like that. The last thing we want to figure out is how efficient was my reaction? Well, if I actually collected 5.6 grams of oxygen, and I should have collected 7.07 grams of oxygen, my percent yield is going to be my actual yield over my theoretical yield times 100. So your actual yield is what you did in the lab. The theoretical yield is the stoic answer. So according to stoichiometry, I should have made and collected 7.07 grams of O2. For a myriad of reasons, I went into the lab and only collected, according to this problem, 5.6 grams. If I take that quotient and just multiply it by 100, okay, that will give me a 79.2% yield. Usually, we want that to be over 90. So if I were doing this in the lab, I'd go back and figure out a different way to collect my oxygen. Okay, so how much excess reactant is left over? I answered that already. 1.2 grams left to. And what is the percent yield of the reaction? If 5.6 grams of oxygen actually collected, 79.2%.